like this flow diagram of the precipitation. Flow diagram of the precipitation. We have the sample. That's a sample that we would like to precipitate. This sample we usually is the solution or the liquid mixed with the small particle or very small particle suspended in the liquid, and then you mix mixture or sample with the precipitating agent. Precipitating agent should maybe polymer. That's right, polymer. The most common chemical. This is the chemical that you add to the sample. Okay. And then after you mix together sample and precipitating agent, that's that. And then you will get the two precipitate and supernatant. Precipitate and supernatant. Precipitate mode is all solid form. This is the liquid form. That's that. You get the clear liquid or supernatant, and then you get the solid setting at the bottom. You can separate this by the gravitational force. That's right, gravitational force, and the solid will be setting down at the bottom. And the clear solution or clear liquid at the top. The clear liquid we call supernatant and precipitate. Okay, for this case, we can separate the very small particle or very small solid or solid that's dissolved in liquid from the solution, and then you get the clear solution. But this is not pure. That's right. Sometimes there are some protein, there are some amino acids, there are some biomolecules dissolved in the liquid, dissolved in the water, dissolved in the solution. You can purify this part by the pasteurization, by chromatography, by adsorption. This is the technique you have to purify. But okay, for this case, we will talk only the precipitation. Precipitation. As I talked to you, the precipitation is make a solute insoluble and aggregates out of the solution. That's why we make solute insoluble. That's right. And then setting out. Setting out is maybe setting out individually or setting out in the group of solid that I call the aggregate. Aggregate means more than one particle. That's right, more than one particle. Segregate together. Like together, it's a bigger inside, something like this. And also we can use the precipitation of the protein. If, for example, if the solution includes only two components, water and protein, okay, you can use precipitation to purify protein. That's right, to purify protein. The primary advantage of the precipitation is inexpensive, because we only the chemical precipitating agent and solution, and also we have the vessel. That's right, you can the vessel, and also the machine to vibrate, machine to mix up the solution. Only this you can operate the precipitation. That means the price or the cost is low compared to the another technique. That's right, and also we can operate continuously and back also. That's why you can operate alternate and back also. Okay, and also we have some disadvantage because the precipitation is quite tolerant of various impurity. Impurity. For example, if we have like protein, amino acid, antibiotic, that's like also 3 of this dissolved in water. But if you would like to precipitate, usually precipitate 3 of these together. That's right, 3 of these together. You cannot separate only protein. You cannot separate only amino acid. Sometimes you have to purify further. That's right, purify further. That usually we use the precipitation at the early stage in the bioseparation process. That's right, in the bioseparation process. Like we would like to separate liquid and solid, for example. And then you can purify solid further, and you can purify liquid further. Okay, the effect that we talk about the precipitation, the first we call is the solubility. That's right. Solubility. If we would like to precipitate protein, we have to know the solubility of protein. Solubility means maximum amount of protein that can be dissolved in solution or in water at constant temperature and pressure. If you know, you can operate precipitation by adjust pressure, adjust temperature, or adjust pH to reduce the solubility. If you reduce the solubility, the solid protein will be separated. How to reduce the solubility? You can add some precipitating agent like this. Okay, the major part acting to stabilize a protein in its native state are hydrogen bonding, like van der Waals interaction, Solubility interaction, right? So Solubility interaction, and also we talk about the hydrophilic, hydrophobic, love water, the sign of water, something like that. Okay, for the aqueous solution, that's right. This force like hydrogen bonding, van der Waals, something like this, tend to push the hydrophobic residue into the interior of the protein and the polar and charged residue on the protein surface. That's what does mean the hydrophobic content, as a hydrophobic content will be put inside. That's right. And also the polar charge or the charge residual charge component will be put in the outside. That means we have right. This is the polar charge. And the hydrophobic include inside it. And then we get the solid, something like this. So it's precipitate. And it's based on the structure and the size of the protein. Like this. This is the protein molecule. And also this is the hydration layer. Okay. This is the water molecule bind to the surface of the protein molecule before the association. And another, like the size of the protein. The size of the protein also is important parameter affect the solubility. As I affect the solubility. This happens when non-ionic polymer add the precipitating agent. As if you add the non-ionic polymer to the solution, that means result in sterilic accretion of the protein molecule from the volume of solution. Volume of solution. For this case, the protein molecule will be informed in spherical solid form, while the polymer is in the form of something like this. Okay. For this case, we will show the equation that describes the precipitation when you add polymer. When you add polymer, you can make the protein in the liquid form or solution form, change from the liquid to be the solid form. To be the solid form. For this case, we can express the solubility or the solution of concentration of protein in water or in solution. In water or in solution. And Cp is the concentration or amount of polymer or precipitating agent. Or precipitating agent. It's a function of the solubility, is a function of polymer. We can see that when you add amount of polymer, solubility will be dropped. Will be dropped or decreased. This is the main reason why we have to add polymer or add the precipitating agent. When you add the polymer or precipitating agent, the solubility of the solution will be reduced. Will reduce or drop. And then the initial concentration and the last concentration is the solubility. You get the driving force for precipitation. Precipitating because it's reduced in concentration of protein. Okay. And then you can precipitate by this technique. And also the solubility is depend on K parameter. This K parameter is a function of radius of the protein and radius of the polymer, RS and RR. That's right. And also a function of specific volume of polymer. Specific volume of polymer. While beta is the constant, we can obtain from the experimental something like this. Okay. And the next effect is the size based on molecular size. This molecular size is known as the group or antibody of the specific molecule or antigen. For example, we have the antibody and antigen interaction. The size is the antibody is the antigen interaction. If we add some antibody to the antigen, but for the antigen, something we add to the solution, the antibody-antigen interaction can form like multi-molecular complex. That's right. And also for this case, we will generate the interaction between antibody and antigen, form the solution, and then we will form the solid and precipitate out of the solution. Out of the solution. This is based on the molecular size. The effect we call this the charge. The charge means if you dissolve solution, dissolve protein, dissolve amino acid, and then this solution, that's right, can split into charge, positive charge and negative charge. That's right, positive charge and negative charge. But for protein amino acid is a special case. We call it the splitter ion. We have the net charge. It's maybe 0 at pi. I will talk to you later. Okay. For this case, the net charge of protein has a direct up on the protein solubility. That's right, protein solubility of increase as its charge increase. Okay. The protein solubility in solution or in water increase with charge. That's right, with charge increase. What does it mean? When the solubility increase, the greater interaction with dipolar water molecule. That means it's higher solubility in water. It's difficult to precipitate of the protein out of the solution. That's right. If the charge is higher in terms of value. Okay. Another repulsive reaction between protein molecule, right, charge for the increased solubility also. That's right. For the technique, the simple way to vary the charge on protein, we can do this by changing pH of the solution. That's right, pH of the solution. If we would like to reduce the solubility, you have to reduce pH, for example. And also for the protein, the minimum solubility occurs at the charge is 0. The minimum solubility occurs at the charge of the protein is 0. We call it the net charge is 0. You have to determine which pH if the minimum solubility. That means we call it the PI, isoelectric point. Isoelectric point means the pH that gives the 0 charge. That's right. That gives the 0 charge. And this also indicates minimum, that's right, solubility of the protein. And then you can separate out the protein in terms of solid form. We call it the isoelectric precipitation. Isoelectric precipitation means you precipitate, that's right, at PI. What does it mean PI? PI means the pH value at 0 charge of the protein, that's right, at minimum solubility of the protein. Okay, for the charge, you can vary pH to change the charge number. Okay. For this case, for example, this is the solubility of insulin. That's right, insulin in 0.1 normal sodium chloride as a function of pH. Okay, the PI is around 5.4 approximately. That's right. This is the minimum is about 5.4. Okay, this is the PI. That's right. PI means the minimum. That's right. The minimum charge is the average for the minimum. That's right. The minimum solubility. This is the solubility. We plot log S, its solubility. We plot log S versus PS. That's right. Versus PS. Okay, this is the minimum solubility, and also this corresponds to 0. That's right. Correspond to the chart is 0 for that case. At 0 chart, at minimum solubility, we call this is PI, approximately 5.4. This is equal to PS. As PS equal to 5.4, the solubility of insulin in 0.1 normal sodium chloride in water, that's that, is minimum. Okay, if you would like to precipitate insulin out of the solution, you have to operate at PS around 5.4. That's right, 5.4. And also for this case, if you increase the PS further, you can see that the solubility is increased. That's right. Solubility increased when you increase the PS greater than 4.5, 5.4. Sorry. Right. And also, if you decrease the PS below 5.4, also the same. Solubility is increased. Solubility is increased in this direction. This is the effect of PS. When you increase the PS greater than PI or decrease the PS greater than PI, the solubility will increase. The solubility increase is hard to precipitate protein. For this case, you can precipitate protein at minimum. That's at minimum solubility. That's corresponding to PS equal to 5.4. This is the effect of the chart of the protein. The net chart of the protein can be determined by the following factor, like the first one, total number of ionized residues, like sodium chloride, like protein, sodium chloride, and ionize as sodium plus and chloride, and something like this. This determined from the ionized residue, and also determined from the pKa or dissociation constant of the ionized group. That's like pKa is mostly found in the with ion compound like amino acid. That's like amino acid. Okay, and also pH of the solution. pH of the solution. The chemical makeup of the ionized group. That's like factor that can influence pKa value also. It depends on the chemical nature of the group, that's like of the group, and temperature of the solvent also affect, that's like affect the chart also. Okay, for the solvent, the first one that we talk about the precipitation. You can add polymer, you can add the chemical. Okay, for this case we talk about the solvent. That's right. You can add some solvent. Some solvent will reduce the solubility of the protein. If the solubility of protein reduces, you can precipitate. That's right. You can precipitate. Okay, the solvent affect the solubility of protein by two parameters. Because it's the hydrophobicity and ionic strength. That's right, ionic strength. Okay, if we consider the monohydric alcohol, this is show you that the methanol is less than ethanol, propanol, and butanol. This is the effect to the solubility. That's right. Solubility. That means at the alcohol with longer acute chain are being more effective. That's right. To the polar group on the protein. That's right. To the group on the protein. Okay. It's a higher effect butanol. Lower effect is methanol. For this case. And also we separate the solvent that affect to the protein solubility. We can separate into kind of salting in or salting out. We can add the salt at the solvent. That's right. The salting in or salting out. Salting in means you add the salt. As you add the salt, solubility is increased as salt increase. And salting out means solubility decrease at salt. That's right. Increase concentration. When you increase concentration of salt, the solubility is increase, we call this is the salting in. This is not precipitation. That's like if you would like to precipitate, you have to choose salting out. You have to check with salt affect the solubility in terms of decreasing in solubility. That's why you have to choose the salt. That's why I show you some. Okay, again, the salting in the salt is very important and it's common used in the precipitate the protein. That's why precipitate the protein. We have two kinds: salting in and salting out. Salting in when you add the salt. That's why add the salt, the solubility of protein increase. This is hard to precipitate. Okay, if we would like to precipitate protein, okay, we have to operate salting out. Salting out when you add the salt, the solubility of the protein will decrease with increasing concentration of salt. Okay, another parameter that affect the protein solubility like the surface. That's like the surface of the protein is maybe non-polar surface. That's like non-polar surface or uncharged hydrophilic or negative or positive. That's right. But it's getting the protein. It also I give you some amino acid. That's right. The amino acid is the compound that consists 3 groups. We have the central carbon, this is for amino acid, and also we have the amino group and carboxylic group. This is the main 2 groups of amino acid: carboxylic group and amino group. And also the third group is R chain. That's right. We have 20 amino acids is important for human body or essentially amino acid. Like glycine is the basic. Glycine is the basic amino acid is the amino group, carboxylic group, and hydrogen add the side chain. That's right. This is the like this small molecule, right? And alanine, this is the CH3 methyl group. Serine, threonine, this is the OS group in the side chain. Valine, isoleucine, and this is the hydrophobic. That's right. Phenylalanine, tryptophan, aspartic acid. Aspartic acid, you can use this as the instead of sugar, for example. That's right. This is COOS. And also this glutamic acid. That's right. You know this common is the monosodium glutamate. That's right. It's the food additive. The Ajinomoto produce the glutamic acid. And asparagine, glutamine, histidine, lysine. This show you the common. That's like common 20 essentially amino acids. That's right. And the amino acid is the building block of protein that I talked to you in the earlier of this class already. And this table shows you the kind of amino acid. Alanine is the percent in the protein, in the side chain, hydrophobic, not hydrophobic. So it is hydrophobic, non-polar amino acid, non-charged. That's right. And also for this case is aspartate. Aspartate is non-hydrophobic and polar. That's right. This is the polar. And charge is negative, like for example. And this is show you the group of amino acid with the non-polar side chain. This is kind of the amino acid with non-polar side chain. Alanine, phenylalanine, that's right. Isoleucine, leucine, methionine 1. This is the example of the non-polar side chain. This is non-polar side chain. We consider the side chain. That's right. For this case, we amino group, carboxylic group. This is the side chain is non-polar. That's right. This non-polar group for valid example. And the next, this is for moderate non-polar. That's like moderate non-polar. This is for polar group uncharged side chain. This is a polar group for amino acid, like serine, threonine, it's like glutamine, for example. This most commonly is OS group. And another kind of the amino acid is positively charged amino acid, like histidine, lysine, arginine, for example. And negative charged amino acid, glutamic acid, aspartic. It's like glutamic acid, aspartic. Okay, this for some kind of the amino acid. Okay, now I will talk to you the technique to make the biomolecule insoluble or technique to precipitate like the protein out of the solution. The first technique we call it isoelectric precipitation. That's like isoelectric precipitation. I talked to you already. We operate at PS equal to PI. That's like at PS equal to PI. At this PS, the solubility of the protein is minimal. It's minimal, and the net charge is 0. That's right. And the second technique we call it the salting out. The salting out means we add the precipitating agent like salt. When you increase the concentration of salt, the solubility of the protein increase, for example. And another kind we add like organic solvent. As like some organic solvent will reduce the solubility, or add non-ionic polymer, polyelectrolyte, and affinity precipitation. Okay, today I will talk only one example, like isoelectric precipitation. I talked to you before like this, when protein charge equal to 0, the solubility is minimal. At this point, we call PI. We call this PI. What it means, PI is PS at charge equal to 0. For this case, you can precipitate by you have the solution. That's why you have the solution. In solution, the protein dissolved in water, for example. If you would like to precipitate by PI or isoelectric precipitation, you have to adjust PS. That's right. You have to adjust PS until reach the PI. That's right. For example, the traditional technique for precipitating protein from milk, like casein. That's like casein. The PS is equal to 4.6. This is equal to PI. That's like this equal to PI. Or soybean. Okay. If you would like to precipitate casein from milk, you can add that PS until it's 4.6. You get the solid casein. That's like the casein. And also the amino acid, for amino acid, it also depends on pKa. You know pKa, you can calculate PI for that case. For amino acid, PI equal to a half of summation of pKa. A half of summation of pKa. If you know pKi, if you know PI, you can add that PS until it's reached PI. You will get the minimum solubility, and then you get the protein precipitate out of the solution. Like this give some example of pKa of amino acid, because PI of amino acid equal to a half of summation pKa. That's right, summation pKa. You can calculate PI from the summation of pKa and divide this by 2. That's right. This is some example of the isoelectric precipitation or isoelectric coil of some protein. That's like pepsin. It's approximately 1. 8 albumin, 4.6. Lysozyme is 11. Hemoglobin is about 6.8. As I did is some PI. Again, PI is the PS that charge is equal to 0 and at minimal solubility. That's like minimal solubility of the protein in solution. Okay, for this case, I give you some equation. That's why we call this the Henderson. That's like Hasselbalch equation. When you talk about the PS effect, that's like when you dissolve some amino acid, some protein in solution in water, That's why we have the ionized compound. For example, like the SA. When dissolved in water, SA will ionize into H plus and A minus. Then you can calculate pH. pH equal to pKa plus log concentration of A minus divided by concentration of SA. Right. If the system know pKa, you can cancel this. That's right. If the system with pKa, you can plus pK for this case. That's like where SA is the protonate species, S minus A minus is the deprotonate species. That's that. Okay, for this case, the equation can provide data. That's right. Provide data to determine the pH at the given ionic condition of the surrounding. If pKa and concentration are known, pH can be calculated. And also you can calculate the degree of protonation or deprotonation. That's right, deprotonation. The protonation means the ability to give pH or hydrogen, the transfer of hydrogen, like this. Okay, today I only talk to you only the first technique for the precipitation is the isoelectric precipitation.